In this video, what we will do is we will see now this kind of new architecture that we motivated from the earlier discussion about simple RNN cell behavior. And if you recall that other video, what we have seen is that when we are actually backpropagating through time, that kind of W matrix was really the key element that defined whether or not we had going to have explosive or diminishing gradients. And in the case of diminishing kind of gradients, the simple RNN had a lot of problems to be trained. And as the gradients dictate how fast we can actually train because of our stochastic gradient descent kind of relationship. So in this video, we will see how we solve this problem. We at least try to solve this problem with this long short-term memory architecture. And in order to start this discussion, I'm going to redraw what we have seen earlier. This is the concatenation of the hidden state at t minus 2 and the current input, which is at t minus 1. We are concatenating it, passing through the W matrix, adding a bias. This is what we have seen in that video as the architecture of a simple RNN layer, and finally passing through this kind of nonlinearity, tan H, to produce the HT minus 1, which is the hidden state at t minus 1. So let me draw one more instance of this unrolled kind of architecture. So we have concatenated now the HT minus 1 with XT to form the HT. Okay, so these are the two instances of this simple RNN architecture that we have seen this kind of problems. So the first step to introduce the LSTM architecture, the first change that we are actually making in that architecture is the introduction of a neural network to form features that are going to be constructed by the network itself. So as we have seen in another video when we looked at the fully connected network architectures, at that time we introduced a very simple network that was consisted just of three neurons, three sigmoidal neurons. And we have actually commented at that time that there is a body of the network and there is the head of the network, and the job really of the body is to create the features which is required by the head in order for the head to actually do its task, a classification task in that case, but also a regression task could also be done. So in a very similar kind of fashion, what we will need to change here is we are going to be introducing, replacing effectively this concatenation and this matrix multiplication and bias addition here with a neural network that it will sort of driven by a sigmoidal nonlinearity. So I'm going to just replace this thing here with the following. So I'm going to have two inputs in this neural network. I'm just continue to draw it like this, HT minus 1. And I'll just going to call it input neural network. And this is, instead of input neural network, I'll just call it input, a dense layer. And we'll write the functional form of this dense layer a bit later. All right, so this is our input dense layer. And the second thing that we need to introduce here in this kind of new architecture, in fact, let me, actually I can draw it over here. The second thing is this kind of line that represents a new memory that is called long-term memory it's also called cell state. So let me write it as a new state. So we had the hidden state ht-1 before. Now introducing the cell state, which will symbolize with the letter S. And so this is the cell state line. And this line will basically represent memory, in a sense that we are able to store a cell state over on that line, that what the line represents, and retrieve it. Okay, so this is we'll see now in a moment what happens. So the input features which are being generated out of the input kind of dense layer are going to be added with the contents of that memory at this specific moment in time. So we are kind of reading out of this memory, and this arrow represents this kind of read operation. And at that moment in time, we are we're bringing the ST-2 from that memory in a similar fashion as we have been using the HT-2 for the so-called short-term memory, the hidden state. So the cell state at ST-1 is being brought in and is being added to whatever input features the input dense layer is giving us to form effectively the new hidden state that will be calling ST-1 at this moment in time. So we have ST-1 here. So the addition of this and the ST-2 is giving us ST-1 that we are going to store into the cell state. Okay, so this is, and then of course the other unrolling time instance, in another unrolling time instance, we're going to form from that hidden, just to finish this, we'll form from the ST-1, we'll pass it through the nonlinearity to form the HT-1, exactly as we were doing it earlier. So I think you can contrast these two kind of diagrams, what we are doing here. So this thing was effectively replaced by the input dense layer. And so we have the new cell state, we pass it through the nonlinearity to form the new hidden state, HT-1. So the hidden state, what we have seen earlier, is a nonlinear function, tan H function of the ST-1. All right, so then we take this HT-1, we pass it through another sort of input dense layer. That's another sort of instance of this RNN. So this is, at this moment in time, our first stage. This is now the second stage starts. Obviously, this requires an input xt. We are summing over, now we're bringing in the memory at time ST-1. So we're reading from ST-1. And see what happened right now. Look at this line. Effectively, we have formed a skip-over connection. This is the skip-over connection. We have seen the skip-over connections in residual convolutional networks, and the rationale there was to solve yet another vanishing gradient problem and effectively allow a so-called highway, which is represented here by this line, which is the cell state, to actually be the conveyor that will transfer this kind of gradient undisturbed many instances in the past. And this is now we're getting somewhere with this. So we are taking again the tan H from ST-1 to form the H of T. So the first changes we have done is the introduction of the input dense layer and this kind of a cell state. And now we need to introduce, so this by itself will actually solve issues with backpropagation, but at the same time, we need to be mindful of a couple of things. The first thing we need to be mindful is that the features which have been generated by the network, we need to make sure that we are able to adjust them in terms of what exactly input features we need at this specific moment in time. So we need to kind of filter them rather than adjustment. We need to filter them. And this filtering is going to be achieved by a gate, what we'll be calling an input gate. And we'll see exactly how this will be added over here in this diagram. Similarly, we need to be treating the both the cell state and also the hidden state over here as resources, because these are basically vectors which we have prior and a priori kind of defined in terms of the vector sizes. And the more we add into them, we do not want to kind of run out of this kind of resource. So we need to treat them as a resource and make sure that we add only the things that we need at this specific instance in time in order for us to sort of achieve the goal. Okay, and of course this goal is going to be produced as if we exactly in the way that we have seen earlier from a specific head that we need to attach to process these kind of states. Okay, so we'll see that in a moment. Okay, so let's try to introduce first our first gate, which I'll call it the input gate. So the input gate is going to be added over here and will take the form of a multiplier. This multiplier is not like the original the multiply. It's called Hadamard multiplication, and in English basically stands for element by element multiplication. So we have, if you like, a vector that it is going to be produced at the input from the input kind of dense layer, and we are element by element applying a factor between 0 and 1. So this input gate is going to end up with being a neural network itself. That it will, as we will see, be represented by the output of by the sigmoid. So that adjustment is going to happen because we are going to be forgetting or not considering inputs, elements, the inputs that are not necessarily relevant to the task. So we are effectively adjusting the contents of this long-term memory. Okay, and so this is, and of course, these inputs will also be driven by the exactly the same instances in time of our inputs, the hidden state and the input xt minus 1. Okay, and then of course we have to do another adjustment. This adjustment will make sure that we are forgetting the elements of the cell state that need to be forgotten, and this will also be called now the forget gate. So for that, how we're going to introduce this forget gate, we will introduce a multiplier that it will sort of be right here. So on this line that takes this st minus 1 and adds it to the input dense layer, to the output of this input dense layer, we will add a multiplier. So this multiplier is going to be the forget gate. So this is xt, and this is ht minus 1. Obviously, there's going to be a multiplier right here too from the previous kind of stage, but and we can actually draw it, but we are not going to decorate it with any variables at this moment. Okay, so we have the forget gate, and finally we need to kind of manage also the short-term hidden state. So what we will do now is we will be adding a multiplier right here. So ht minus 1 is obtained after this multiplication with, again, these multiplications are the so-called Hadamard multiplications or element by element multiplications. So this is going to be called the so-called output gate. And this will be the xt ht minus 1. Okay, and this is basically all the changes, at least in terms of block diagram, that we would like to introduce. So this whole thing here, from the moment we have, and so let me also draw it over here. So we have a multiplier, and this is ht, which is exactly the same nature as the output gate we just introduced. And this is xt, sorry, this output gate is ht minus 2 xt minus 1. This output gate is xt ht minus 1. So these are so what we will be calling from now on is this thing over here, this block, we'll be calling it the LSTM cell. And we can actually contrast it with the simple RNN cell that we had earlier. So these are all, at least in terms of block diagrams. So let's try to bring a couple of examples to understand, a little bit the function of the input gate. And so let's write it down. So the input gate is learns. Mind you that we have parameters here. So this input gate, output gate, and forget gate are all neural networks. So during the training, the parameters of this gate will be determined. So to learn to determine whether or not the input xt is worth preserving. So for example, just to give an example here, let's say in one sentence from sort of natural language processing, let's assume that we have a task that has to do with text summarization. So in one sentence, we say that the bank introduced a new savings account So in this case, the input gate will be such that it will kind of remember everything. But in the case where, let's say, the sentence is the bank, comma, faced with criticism. Over interest rates, comma, introduced, and so on, a new savings account. So this part, criticism, faced with criticism over interest rates, is certainly for the task of tax summarization may not be needed. And so therefore the corresponding elements of the vector, which is multiplying, if you like, the input features, may be such that they will need to be close to zero, and therefore not necessarily being stored in the sort of cell state. That's a basically simple example of remembering exactly what the input gate will be doing. So the forget gate is again learns after the training process to remember exactly what is needed to be preserved in multiple instances in time in terms of cell state, and the output gate is doing that for the hidden state. So I hope that this is kind of clear what kind of changes we have introduced in terms of block diagram. And in terms of equations now, let's write down the equations so we can actually get to appreciate the parameters that we have introduced. And there are plenty of parameters, and therefore LSTMs are kind of complex structures because of that reason. The hope is that in the back propagation we'll be able to preserve better the gradient. So if you look at the back propagation, you actually start with and imagine that we also have a loss, and this loss, it is effectively obtained by attaching a head on this hidden state h of t. So that loss is going to result into the a downstream gradient, but this downstream gradient, as it enters over here, it finds that skip over connection, and this skip over connection passes through uninterrupted. Of course, we have this multiplier over here, and this uninterrupted sort of path is the one that we are going to be using so to go back in time. So we will go over here, we will see another tan h function, sorry, another summer, and we are going to pass through the input kind of dense layer, but the other path is to go over another skip connection. So if you unroll the skip over connection diagram, just like in the same way as we have done in residual kind of networks, then you will actually see that we have a multiplicity of paths again to go over the various kind of stages. So the diversity of gradient flow is preserved. So that is the sort of rationale of introducing, if you like, this highway. And that's the reason why these architectures are instances of what we call highway networks. Okay, so that's that is a block diagram, and now we can actually go ahead and see how we can write down the equations. So the equations are presented to you in the site. So in the site, to understand the backpropagation through time for these LSTMs and how it contrasts what we have seen earlier with the simple RNN, and demonstrate that we can definitely have some hope to remember kind of a longer periods of time in the past and avoid this so-called diminishing gradient kind of problem. Let's kind of draw a diagram sort of showcasing the skip over connection. So in this kind of diagram we have the cell. So this LSTM cell was the one that we have just drew earlier with all this kind of forget gates. But for now, what I will do is I will just leave all this kind of multiplication, Hadamard multipliers with the gates kind of behind, and go back to this original diagram we have seen where if you remember, we have some state st-1 that was going through the tanh function, and we had this kind of input dense layer. And what we were doing is we were taking this st-1 with a skip over connection and we're adding into the input. And then we had another block that consists exactly of this function. And this effectively, what reminds us, this is st right now. So we are doing this in order to add it and form the new cell state, which is st+1. And so on and so on. So this is exactly what we have seen earlier in another video in the set of residual networks. So we can actually go ahead and unroll this diagram and create yet another diagram. We have done already exactly the same process in the residual kind of network video. So for those who have missed it, you can consult that kind of video to see exactly how the unrolling process was demonstrating the fact that during backpropagation, where we have some kind of gradient that it is flowing backwards, then that architecture with the skip over connections was allowing the gradient to flow over this path, in fact, a whole diverse set of paths. And one of them was a direct skip over all of the stages that we have seen here. So there is in good faith, we have the ability to maintain this kind of gradient flow over many stages. Now, in practice and empirically, because we have introduced, the gates, the inputs, the gates, gates which are associated with the forget gates and so on, as well as also other practical kind of considerations, we are going to be unable to maintain this kind of gradient over long periods of time. So empirically, what we have shown is that although LSTMs improved what we have seen earlier from simple RNNs, finally themselves are also suffering from finite memory. So we don't expect miracles here, but at least we have some a better situation compared to the simple RNNs. And then for this reason, LSTMs are used instead of simple RNNs for any use case that requires them. So back to the textbook, the course side, that is, we are going to, we're actually seeing here the diagram of the LSTM cell. And I think the picture is slightly different from what we have seen just now. But it does show all the trainable parameters in this full version. So we have the input dense layer that we have seen. This involves a tanh nonlinearity typically. We have the forget gates. This is the input forget gate with all these trainable parameters. The cell state, this is the input forget gate. This is the cell state forget gate with another set of trainable parameters, and the output forget gate with yet another set. And this actually diagram kind of shows the cell as we will need to implement it in software. And this is effectively what the APIs of both PyTorch and TensorFlow are implementing. Evidently, we have a fairly complex structure, but I hope you recognized, how if we break it down into its parts and just treat the essentials, how the structure kind of serves the purpose of having us to surviving in a longer periods of time, that kind of gradient. Now, in terms of equations, effectively the diagram just shows these equations. But there is another reference. Unfortunately, we are not really able to do the animation right now in kind of this kind of format of writing. But there is a YouTube video that is the reference for, which I believe it's a kind of a useful video to go through because it just shows a very, very simple use case and kind of demonstrates how the gates are helping us in that kind of simple use case. It has